Okay, welcome everyone. We'll go ahead and get started briefly here. I'd like to thank everyone for coming to the retirement colloquium for Dr. Howard Bluestein. Many of you have interacted with him for his long career here through the University of Oklahoma. Howie was in service to OU for 47 and a half years.
48.
48 and a half years.
It seems like 40s.
I got the number from your retirement letter, so 48 and a half years, retirement effective in January. Many of you may have been taught by Howie over the years. Of course, he's had a tremendous impact on the Norman weather community over his career. Much of the use of mobile radar observations of storms and tornadoes today was inspired by a lot of Howie's leadership for many decades. Howie, I think you have 4 books that you've written.
I think there are 5.
Maybe
I show them later. I'm not sure.
Okay. So, a lot of textbooks, over 160 journal articles. Obviously, well known and regarded as an expert in the study of convection in a very broad sense, but also in use of radar to observe these storms and tornadoes, especially. And in that career, he's published many papers. I looked on Web of Science. Your highest cited paper was on squall lines, which was published before I was born. And for me personally, Howie was one of the 2 faculty mentors that I had when I started at OU. And if I could boil his mentorship down into one clear and simple guidance that he gave me, was that it was very important that whatever I was doing, that I was passionate about the work that I was doing, that I just didn't enter into things because I needed to get grant money or I needed to do X, Y, and Z just to establish myself as a faculty member, but to enjoy what I was doing. And I think what would be clear from the end of this talk that he's enjoyed his entire time in that similar role. So, Howie.
Thank you, Cameron. It's great to be here. And as Elaine Stritch has said, I'm still here. If you know who Elaine Stritch is. The title of my talk comes from a Bob Dylan album, My Back Pages. So I'm going to talk a little bit about what I've encountered on the light side, on the more serious side, and I'm going to have to really rush. This is a painting by Paul Gauguin, and it's entitled Where Do We Come From, Where Are We, and Where Are We Going? And I'm going to try to do that with a personal pronoun of one, not many. I'm going to begin a long time ago. That's me in the early 1950s, probably looking at a cloud. Then I'm at my father's graduation, wearing a graduation cap, so that probably I was anticipating an academic career. Then I was playing in the snow. Boy, did I love snowstorms when I was a little kid. We moved to South Miami Beach from Boston, and I took up shell collecting. And you can see in the lower right-hand corner some of my drawings. And then there was the Worcester tornado in 1953. And I remember I was outside playing, and my mother told me to come in the house. I've told the story too many times. And I said, why? And she said, well, it's a tornado, and they take little boys, and they suck them up. I didn't care. I wanted to stay outside and see it. I did some drawings when I was young. The lower left-hand one is a pencil sketch from probably around the 3rd grade. I think it's an equine storm chase. I don't know what I was thinking when I drew this. And the picture on the right is a pencil sketch of a tornado in Mamatis. So I was thinking about tornadoes even when I was extremely young. Here's a diary entry from 25 June 1959. And I'm having trouble. Oh, here it is. I can read it. It says, at night, had a big tornado in Miami. Daddy drove me out to see it. On the way back, it was pouring rain, 3 feet of water in the street. How could that not capture your attention? When I was in junior high school, I did a lot of work with ham radio, and there's my ham radio gear. And in the upper right, I began to develop pictures. I worked in Doc Edgerton's laboratory at MIT. He's the person who made the famous photograph of the milk drops splattering. I didn't work with him, but with other people. So I learned how to develop my own pictures. In the lower right-hand corner is a laser and optics for Fourier transform holography, and that became my bachelor's thesis. I'll say a few words about that. While I was a junior at MIT, I worked on the computer-aided design for the Apollo guidance computer at the MIT Instrumentation Lab. They gave me a secret clearance. I don't know how that ever happened. I must have gotten mistaken for someone else. But it was a lot of fun. But this was working. My students know my computer abilities, or lack of them. This is before software, and we were actually designing transistor flip-flop circuits that were on or off. And I was doing that in a sort of a rote manner for the Apollo guidance computer. It was a lot of fun. I got my bachelor's degree in EE on the restoration of motion-degraded images. So if you take a photograph and it's blurred because the camera moves or the person moves, I can use Fourier transforms to go ahead and reconstruct the picture. Then I got a master's in meteorology and EE, prediction of satellite cloud patterns using spatial Fourier transforms. Fred Sanders and Ed Lorenz were my co-advisors. And, come back over here. And I must say that Fred Sanders tried to get me to publish this. And I said, why? I don't care. I want to move on to the next thing. And I should have published it, but never did. Never even tried. I got my PhD in 1976, synoptic scale deformation in tropical cloud bands, and under Fred Sanders. And this was inspired by work that happened during BOMEX, the BOMEX experiment, 1968, and GATE. Say a few words. I want to show you a few of my early photographs. These are black and white. And in the upper left-hand corner, you see a line of towering cumulus over Boston from the Green Building. In the upper right, you see Sha-Na-Na, which is an oldies group at the Boston Tea Party. In the lower left, I took a picture of what I thought was just fog, and now I recognize that there were boars down there. Didn't know that then. Then Ted Kennedy, who was our U.S. Senator, and a Grateful Dead. I'm actually behind them, looking down on all the people when there was a big strike during the Vietnam War, and I went up and got behind the Grateful Dead and took a picture. And some of these pictures appeared in the MIT newspaper, the text. Then in 1971, Joanne Simpson, some of you may have heard of Joanne Simpson. I hope you have. She took me up on a randomized cloud seeding experiment she was conducting, and we flew in and out of thunderstorms over central Florida. Boy, was that fun. In and out, in and out. And every time you saw the cumulonimbus tower approaching, you knew you were going to get a jolt. And after that day was over, I said, well, this was fun. I've done it. Not going to do this again. Low right-hand corner, you see a picture, a drawing that I made also when I was probably around the third grade of an airplane going into a big cumulonimbus cloud. So I guess maybe I presaged this. Then in 1971, lower left-hand corner, Joe Golden took me up in an airplane, and we went looking for water spouts in the Florida Keys. And there's a water spout, and it's right next to a curtain of precip. Something interesting might be happening there. And in the upper left-hand corner, I took a picture from the roof of the computer building, which is where the National Hurricane Research Lab was, where I used to spend summers. Before I went to Boulder, I used to go down to Florida. Any place that had convection, I would go. And again, you can see the water spout and a rain curtain. Something's going on there. And that's a picture of me along with a time-lapse movie camera. And I'm not going to explain anything else. In the upper left-hand corner, in the MIT meteorology department, we were very serious people. We stuck to our work. We had a betting board. This was off-track betting. And you can see all sorts of bets. We bet on everything that moved meteorologically. The maximum wind at Logan Airport, the total precipitation. There's one that I wrote that says, water spout at Miami, the season lingers, Howie Bluestein. Anyway, we had a lot of fun. About that time, my photographs that I'd been taking since from 1970 to 1973, they had their first exhibit in Building 10 of MIT, which you can see on the right. And I was excited about that. And then on the left, when I came here to OU, we had an exhibition at the OU Museum of Art. And I'm sorry that I was not dressed very well. And then in 1987, at a radar conference in Boston, some of you older radar people might remember this, but they had a session called Radar and Art. And a number of people and I submitted beautiful radar images. Here's more tornadoes in art. Just want to show you the big wind in Georgia, which looks to me like an anticyclonic tornado, except for a tree in the background that's going the wrong direction, so I don't know what's happening. There's a famous picture by John Stewart Curry, which you may have seen, about John Brown, the abolitionist. And actually, during the vortex experiment, we spent one night in Topeka, Kansas, and I wanted to see the original, which is in the Kansas State Capitol. And we couldn't get to see it because there was construction. I was very disappointed. I have to go back there someday. Lower right-hand corner, there's the Miles Davis album with a water spout. And I'm not showing it here, but the Art Museum in Minneapolis, there's an incredible photograph and painting of a tornado over Minneapolis a long time ago. I think it's during the 19th century. And then finally, I want to mention that when I first came here, well, in the early 1980s, we got a call from the Talking Heads member Jerry Harrison wanting a tornado photo for an album cover in the early 1980s. And that never happened, but boy, I would have loved to have had something in the Talking Heads album. Okay. Then, in 1974, I participated in the GATE experiment. You all, at some point, should participate in a field experiment. Chasing here in Oklahoma and so on, but you should do all sorts of other things. Whenever you can, it's a great experience. I went out on a research vessel for about, it was over a month, and I ran the radar. I had an 8-hour shift with Speed Geodis, and I had my first taste of running a radar. And here's someone who runs a radar coming in right now. And looking at the radar and then going outside to see the actual storm. And that was fantastic. I knew I had to do something. So there's a water spout. And Joanne Simpson took this picture and used it in a paper about water spouts. On the left-hand side, you see some convection in the ITCZ off the coast of Africa. And there I am at a younger age. Okay, up left-hand corner, you see the day of I graduated. I successfully defended my PhD thesis, miraculously, and there you see Ed Lorenz, and behind Ed Lorenz, you see the teletype machine, and there's Fred Sanders, and then to the right is Jane McNabb, and I don't know who the woman was. I actually don't know who she was. And then to the right, I came to Norman in the late summer of 1976, and I decided to embrace the local culture. Briefly, I began storm chasing for Jeff Kimple, and I'll say a lot more about Jeff Kimple later, for the NSSL-OU Tornado Intercept Project. And the object was to provide ground truth observations for the NSSL Doppler radar. So I was part of the very, very large effort to correlate what you're seeing in the Doppler radar with what's actually out there. Do you guys see a tornado? No. Well, we're seeing a mesocyclone. You guys getting hail? Well, yes, we just lost our windshield. And it went on like this. Everyone would go out and do this and then try to take movies. I knew nothing about storm chasing as a student at MIT, but I did go out with friends of mine around the Boston area to chase storms. And ask me about that later. We didn't see very much, a lot of gust fronts. But I remember hearing someone tell stories about rotating storms in Oklahoma. I thought, wow, that sounds exciting. My first tornado was on May 20th, 1977. You can see the original slide in the left and my digital remastering, so to speak. This was a big tornado. And I got to see this again by accident, because for the whole experiment, I was the low person on the totem pole, and everyone else was out in the Texas Panhandle seeing tornadoes day after day after day, and I never got to see one. Finally, we had a big outbreak day, and they said, okay, Howie, we're letting you loose, go, and we saw this. Okay, some early tornadoes, the big Wichita Falls tornado on April 10th, 1979, and you see the Seymour tornado going into its rope stage, and the red arrow points to where I think the Wichita Falls tornado actually began. Up in my office, among all the other junk, I have actual debris, I have canceled checks and student notebooks that I picked up on the ground northeast of the tornado. I still have that. And then on the lower right-hand corner, there's Brad Smoll and Bob Davies-Jones. For you who do severe storms research, know both of these people by their journal articles, and they're having a good time. Okay, more local pictures. Upper left-hand corner is the map room in the engineering lab. You can see the teletype machines. In the lower left is Brad Smoll and Eric Rasmussen looking at our displays. Chris Soule was my first master's student who actually got his thesis published. Lower right-hand corner is the chair who was here when I arrived, Rex Inman. And in the upper right-hand corner, thanks to Pat Kennedy, is a picture of the facsimile maps hanging on the wall. There's on the upper left is Lou Wicker, a great supporter of mine. And lower left-hand corner is Dan Rusk, and I were just acting like good old boys. We were not drinking whiskey and rye, though. And in the right is Eric Rasmussen and Dan Rusk posing, and what am I doing? I'm grazing in the grass. You have to when you're out there. Upper left-hand corner, we used to have a great time. Fred Carr used to lead an Andrews Glacier hike. We'd hike up to way above timberline, and then we'd slide down a glacier. And that was great fun. You can see a lot of people up there. In the lower left-hand corner, I was the first university COMAP instructor, along with Brad Coleman, who was the first National Weather Service instructor. And then you can see Ed Berry, who no longer with us, unfortunately. He was one of my master students. Then in the middle, you can see my office at the engineering lab. And it looks like my office now. It's a mess, a holy mess with some pictures up on the wall. Upper right-hand corner, this was sent to me by an unknown student. What am I doing? Well, I'm lecturing out the window. When I would lecture in a room that had windows, I would spend a lot of my time looking out the window. And finally, the students got fed up with it. So they said, I came into class and they turned the chairs around so that I would have to lecture at the window. In the lower right-hand corner is one of the students came in, and there was this horrible thing staring at me. He made a snowman of me. Don't ask. Steel wolf or for a beard. Dusan Zernich and I, in 1994, after a conference, had a wonderful weekend north of San Francisco. And we stopped. I insisted that we stop in Bodega Bay, and I did a recreation from The Birds, from the Alfred Hitchcock movie. And you can see I'm terrorized in a phone booth, and you can see a bird coming by. On the upper right-hand corner, this was taken in May 1988. Now, 1987 and 1988 were two of the worst chase seasons we have ever had. And so the students decided to have a wake. And on the lower left-hand corner, you can see, shaped like an omega, it says 1987 storm season died while hosting a block party. Lower left-hand corner, a tornado picture that I took that was going on in Gold Hill, which is about 10 miles or a little bit more northwest of Boulder at high elevation. And I took it from downtown Boulder. Interesting story. Kathleen and I had gone out to Lucille's restaurant, and I was going up the hill, and a hippie, a real live Boulder hippie, came running down the hill, had no idea who I was, and started yelling, "Hey man, you want to see a tornado? Just go up the hill, man." So I went up, and my God, there was a funnel cloud, and it was a real tornado that did damage. The other picture of me, we have a lot of fun when, especially when nothing is happening. This is not a doctored picture, but I was inspired by the famous picture of Mao Zedong swimming in the Yangtze to show how healthy he was, and it was obviously a fake picture. So I decided that I was going to get to a sea of wheat. And then finally, there's a picture of Fred Carr wrangling some kelp at a Silmar at a meeting. More pictures. Gene Lee at NSSL, Don Burgess, and he's no longer with us, unfortunately, Dick Doviak. You probably know of Dick. And then you know of Chuck Doswell. And then on the right, upper right is Ed Kessler, who was the first director of the National Severe Storms Laboratory. And Ed Lorenz and I were looking at weather observations. Some of you may not know, you know of Ed Lorenz and his work on chaos theory. Ed Lorenz was a real weather enthusiast up there with the people that we chase with. He was just a real fantastic weather person. And we would go hiking, and instead of talking about predictability, he would talk about weather for hours and hours during our hikes. Absolutely wonderful. Ed Lorenz is the person who got me to come to Norman. Ed Lorenz and my advisor, Fritz Sanders, were together in the 1950s at MIT. And Ed said, Ed was on sabbatical at MIT. He was next door to my office. He knew I was excited about severe weather. He said, Howie, you have to come to Norman. And I said, Ed, I wouldn't go to Norman for the last place on earth. Because to me, I had the mistaken impression that Norman was like the Texas Panhandle during the Dust Bowl days. And when I was invited down here to the university for an interview, it was in June, and a big MCS came through at night. Well, that did it. I mean, I'd never seen anything like this. I don't care what's going on. I'm coming down here. And then you see Dushan and me just last year. Kerry Emanuel. Kerry, you may not know, but came down here in 1979 to Chase. And he was the first Sims employee, right? And he took a fantastic movie. We didn't have videos back in those days of the Orienta tornado, multiple vortex tornado, May 2nd, 1979. There's a graph over here, and it kind of ends. I don't know. Terry's going to have to explain what that is, but something nonlinear was happening. And I was the Houghton lecturer at MIT for about 6 weeks or so. In February of 1999, it was Eddie Nelson, who used to bring out all the teletype paper and facsimile machines. And then there was Speed Giotis and Pauline Austin, who really had a tremendous influence on me because Pauline Austin was in charge of the radar. And I know Josh is here, and I think, Josh, you probably had a lot to do with Pauline Austin also. She was absolutely wonderful. I can tell stories. I won't right now. There's not enough time. More pictures. 1996, Greg McGilvery shot an IMAX film that we were in, and that was a lot of fun. We didn't get any tornadoes. The tornadoes that appeared in the movie were from the pilot that we were shot like 5 years earlier when they came out here. And one of my favorite places to go skiing in Steamboat Springs, and you can see that there's a vortex and a tornado lane. If you're ever up in Steamboat, be sure to take Tornado Lane. It's a blue trail. Let's see. We have a picture of a buffalo crossing in front of the radar truck in the Wichita Wildlife. And then in the lower right is one of the most poignant things I've ever seen while storm chasing. This is on May 16th, 1999, and I know that Robin will remember this. You can see the W-band radar. We stopped, and we were looking for tornado damage, and there was hardly anything out there, but we found a tree that had damage. But you notice that there's an isolated grave marker. And that grave marker says baby. It has the person's name, died October 24th, 1904, age 3 months and 9 days. And that just got my heart. And I still look at this, and it's pulverizing to me. Okay, we also did some art in front of the old building. There was a dragon sculpture, and I'm kissing a bear sculpture. Those were in the days when it snowed here in Norman. Okay, we moved from the engineering lab to the SEC to the Sarkees Energy Center, the new building, and you can see that it looks like my current building and the old building, just an absolute mess. And then my good friend and colleague, Lance Bozard, who is doing an imitation of me, doing an imitation of a thunderstorm with a penetrating top and anvil. Jeff Kimple and me. Jeff Kimple was an amazing chair. He became the dean, then he became the provost. And then he was director of NSSL. He did all those things. And I can tell you, as a person, as a mentor, he was absolutely fantastic. And let's see some random pictures in the lower left. There's Bob Schlesinger from University of Wisconsin wearing his nested grid shirt. For those of you that don't know what that's about, I can tell you later. And then there's John Brown, my good friend. We used to climb 14ers. I've climbed 29 of the 54 14ers, and a lot of them were with John. And we would go up to Kathleen, my wife, hates this, but we would climb a 14er or anything, and we wouldn't go down until we heard the first thunder. Not smart, but. And then there's Reed Timmer with his dog and me. Reed took my classes a long time ago. And then a more recent picture where we're waiting for Godot. Nothing was happening in that day. Okay, these are the scientific problems related to supercell tornadoes. And the ones that we have addressed are in red: the relationship of the tornado to the parent storm, the relationship of the parent vortex to the surface boundary, vertical variation of the winds, especially near the surface. This is important to civil engineers. The wind structure at constant elevation, and then the observations, Doppler radar, Doppler LiDAR, especially mobile ones. First thing we tried to do was make in situ measurements in tornadoes. We devised a device called TOTO, the Totable Tornado Observatory. It weighed 400 pounds. There's Al Bedard, who actually made the instrument. We began making in situ measurements with support from NSF and MODOS and NOAA. Very difficult to do, sometimes dangerous. Here's a TOTO deployed in front of a tornado at Altus Air Force Base. Tornado came towards us, dissipated. A new one formed to the northwest and moved to the northwest. What are you going to do? 1981, there was the big Binger tornado, and my students got this out, and you can see the mesocyclone. The center of the tornado passed to the west, and it's probably a good thing that the tornado passed to the west if you look at that tornado. In 1981, I joined a project in which we used the NASA Airborne Doppler LiDAR, and we made measurements in Oklahoma for just a couple of days, and we made measurements in gust fronts and cumulus clouds. And in the lower right-hand corner, you can see from my student at the time, Bill McCall, who's also no longer with us. And you can see we did a very nice job of mapping the gust front in clear air. And I thanks to Dirk Joviak for getting me into this project. And I must tell you that we wanted to do this again, but the NASA plane burned on the ground, and that was the end of the plane, the LiDAR, and the project. 1984, I took a sabbatical. It was then called the National Hurricane Research Laboratory. And at the lower right, you can see my good friend Bob Burpee and Bob House from the University of Washington and Frank Marks. And I flew a number of hurricanes. I flew Hurricane Dawn in 1972. I flew Hurricane Diana in 1984. And we also flew Norbert in the Eastern Pacific. And this is the picture I took inside Hurricane Diana, and I was just amazed. It was so beautiful. And you can see the haze in the lower left-hand corner. You can look right down at the ocean, and you'll notice that the convection are pointing towards they're pointing up and to the right. This is the direction of the shear. The winds are strongest down below, weaker left. The shear is backwards. Oh, and anyway, we did a paper. We compared the visual convective elements with what we saw on radar. Then I decided, well, why don't technology had evolved to the point that you could release soundings using these small shoebox size instruments, and we did that, and it was inexpensive, and we had no winds. So Bill McCall used the optical theodolite to track the balloon. That's how we got our winds. Then, let's see, the middle picture, Los Alamos, 1987. I and other people from the department were on a NOVA program on tornadoes in 1985, and it was widely viewed. And an engineer at Texas Instruments in Dallas who had worked on a particular radar at Los Alamos contacted me and told me I needed to contact a person by the name of Wes Unruh, who had a radar we could use. We can't tell you what it can be used for, but it can detect helicopter plates. So I went down there, and there was a FMCW low power, battery operated radar. And I'll show you, we used it to make some of the first measurements in tornadoes by going close up. Lower left-hand corner, some of these pictures are random. Picture of Ed Lorenz and me up in Paiute Peak. I don't know how many of you go hiking in Colorado, but you go up Mount Audubon, which is 13.2, something like that, 13.3, and you come down a saddle point, and you can go up Paiute Peak. Then we came back down and went back up and came back down. A lot of fun. And then in 1995, so my picture is from 1996, Josh Werman was a faculty member here, and his office was just a few doors down from mine. And he had the idea to put a radar on a truck. Talk about that in just a minute. Then there's a photograph that I took that appeared on the cover of Time magazine, and in the spirit of Mad magazine, it was only $2.95 cheap. Some of you don't know what I'm talking about. And when Twister came out, there was a lot of publicity for Twister. So this is one of the highlights of my life. I think one of my photographs appear on the cover of Time magazine. Okay, we released soundings, and one of the things that we did, we released a sounding into the updraft of a tornadic storm. And from the hydrostatically computed height and so on, we calculated the updraft speed. And it's kind of matched parcel theory, which it shouldn't have. We got this published. Anyway, it was a nice try. Then I had a project which I got funded from NCAR and NSF, which I called Class for Class. Class in capital letters is an acronym for the Cross-Chain Lorraine Atmospheric Something System. And so we used Lorraine navigation. We now use GPS, of course, to track the balloon. And we did that, had a lot of fun. Students loved it. I was involved with the first successful attempt to do an airborne Doppler analysis of tornadic supercells during the COPS 91 experiment. David Dowell was my graduate student. This was part of his master's thesis. Dave Jorgensen, who used to be at NSSL. And you can see a picture of the storms that we probed, and I won't go into any detail. But David Dowell went on to analyze the McLean, Texas Vortex 8 June 1995 storm from the Eldora Doppler radar. This was from the P3. And he had a detailed description of cyclomesocyclogenesis. That's a very, very highly referenced paper. Dowell and Bluestein, 2002, A and B. One day I was jogging in South Base. I used to jog every day. And I noticed this, it looked like an old radar. And I looked at the truck and said, Department of Commerce Weather Radar, Weather Research Doppler Radar. It's a piece of junk. And I remembered that in 1957, there was a radar that looked just like this that had probed a tornado in Dallas, Texas. And it was one of the first CW observations of a tornado. And I took this picture, and I think this is it. But I can't swear to it. Low left-hand corner, you see me chasing the easy way at NCAR. You just go up to the tornado simulator. You grab a hold of it. Tim Marshall, who is a very, very famous chaser, and me. And then finally, Fred Sanders with a voodoo doll, and Lou Wicker with a real smirk in his face. He was up to no good. And the map, and the movie camera. But anyway, it was a great time. We did science and we had fun. Upper left-hand corner is the Vortex team that had the W-band radar, and I can see a number of people there. And lower left-hand corner, my students and a few other people. I think this was the Severe Storms Conference in Madison. And then the lower right, it's Fred Sanders students. And you can see Bob Burpee was a student, Lance Bozart, Brad Coleman, John Brown, John Jocham, and me. Okay. All right, so Bob Crane was a faculty member here, and he suggested to me that you put, NSSL had a Ka band radar that wasn't being used. He said, why don't you take it and put it in the truck? And I said, oh no, That's too difficult. I don't want to do that. And then Gene Moore, who was kind of an early version of Reed Kimmer, an excellent chaser, he had mentioned something about someone having a radar that they were going to take out. But then Dusan Zernich, and I didn't really think about this, but Dusan and Don Burgess and Larry Hennington had a paper in which they used, I think it was the Cimarron radar, and purely by serendipity, they had a tornado come by, and they collected data which allowed them to compute the spectra very, very well in a large tornado. And I'm going to take a quote from this paper. These authors believe that high priority should be given to the development of a portable Doppler radar, which could be transported by intercept teams to the tornado. I didn't know about this. Maybe Josh knew about this. It just seemed like a good idea to try to do this. So I talked to NSF, and they told me that, well, UMass has a W-band radar. Why don't you talk to them? So I talked to the people at UMass, and we got funded, and they put a W-band radar in a truck. And it was difficult to use. And a lot of the problem was that attenuation was horrendous at W-band. But we did get some good data. But Josh Werman, around 1995, probably started maybe earlier than that. He took two old NCAR radars, I think it was CP3 and CP4, put it on a truck. So what I thought I didn't want to do, Josh did. And it turned out that those radars and the subsequent radars are the most durable, probably most used mobile radars up through today. And the X-band radar was great. You didn't have to worry about attenuation. But you had to get pretty close to get high spatial resolution. The W-band radar had a half-power beam width, I think it was like less than 0.2 of a degree, as opposed to 1 degree for the Dallas. Okay, while we were out, I'm going to show you a video that I took back in 1991 while we had the portable radar out. I'm just going to zoom on ahead here. We don't want to see the whole thing. But this was an amazing tornado. And we sat in one place for a long time to watch the tornado cross the road. We answered the question, why did the tornado cross the road? To get to the other side, obviously. But that is one beautiful tornado. I couldn't put my video camera on a tripod. It was too windy. And I was a little nervous. This chaser going the other direction, smartly. Okay, you get the picture. It's a big tornado. Oh, let me just go back for 1 second. And there you can see Herb Stein, who is also no longer with us, who was our driver for many years. Okay, some of our, I'll better start breezing through this. Jim Ledoux, Doug Spahager, Herb Stein. We collected data in a number of tornadoes in CW mode, so we have spectra. In the Red Rock tornado in 1991, the noise level was about 100 meters per second. So I think we measured wind speeds of 100 meters per second. And in the lower left-hand corner, we advanced from CW to FMCW, so we now could get spectra within range. And here you can see a three-dimensional plot of the spectra as a function of range. The tornado is down the lower center. In 1993, I did something completely different. Decided to go up with Joe Golden in a helicopter, a NOAA helicopter, and we went after waterspouts. Boy, is that ever fun. You know, in the helicopter, you just get wherever you want to go. So we went, we saw many, many tornadoes over a 4 or 5 day period. This is one looking straight down, and you'll notice there's no tail. The waterspout was stationary. Now, I showed you pictures earlier which shows waterspouts with a rain area nearby. So that would argue, well, you need a gust front, okay? But these were different. You looked around and you couldn't find any precipitation. What was going on? And if there's a boundary out there, you can usually see it in the sea surface. But if you look at the picture carefully, you can see there are dark areas and light areas. There are reefs. And I'd be willing to bet you that if you could measure the sea surface temperature, that there were variations in the sea surface temperature. I don't know whether that was related to tornado formation or not. Anyway, you can look in the BAMS article we had. And there I am in the upper right with a flight suit. Well, why was I wearing a flight suit? Well, I was wondering too, until I got up there. You're sitting in an open helicopter at cloud base, dry adiabatic lapse rate, and it's pretty moist. Well, at the surface, the temperature is something like 85 or 87 with the dew point is 75. But you're at cloud base. It is freezing. It's cold and wet. And there's, see, Joe Golden. He had his legs dangling out the helicopter. Now, we then used the UMass X-Pol, which was an X-band radar modeled after Josh's, was polarimetric. And we took it out, and on the upper left-hand corner, you can see some W-band observations we made in some tornadoes. And what you do is you take RHIs through the tornado, and you looked at it and said, oh my God, it's hollow. But right near the ground, it's not hollow. And we think what's happening is you're getting centrifuging of the large particles above the ground. But right at the ground, near the ground, the frictional inflow is so strong that it's bringing the particles back. And we have many, many instances of this. And then Robin Tanamachi, in her PhD thesis, took data that we collected with UMass X-Pol in the Greensburg, Kansas tornado. And there you can see a weak echo, what Robin called a weak echo column. It's taking a weak echo whole to 3 dimensions. And it goes up to the top of the storm. I mean, that says that if you were to actually be up there looking down, you might be able to see the ground. It's hollow. There's a story that goes along with this. I'll tell it very briefly. The radar broke down. We had a flat tire. We had no spare. We were in the middle of nowhere. It was a great day. There were tornadoes going on back in Oklahoma that we were missing, and I was tearing my hair out. And that's why my hair turned gray prematurely. But atmosphere has a way of getting back. And what happened was that I called up AAA in Dodge City. They hauled the whole thing to this town called Protection, Kansas. They found a good tire, put it on. By that time, it was too late to do anything. So I said, you know what? We have some splitting storms to our south. Let's just pick one of them and make sure the radar is working. And Robin was great on this day. So the police gave us an escort out of Protection to find a high spot, a good spot. As soon as we turned the radar on, tornadoes started forming. What more do you want? I mean, there is a God up there. And I said, let's not go after it. It's getting dark. So because of that, we were able to get the whole life history of the tornado, and it went through the town of Greensburg and did a horrible job on the town. Terrible. But that became Robin's PhD thesis. Oh, there's a picture of Happy, Texas. That's you see the data in the upper left-hand corner. That has a Chuck Doswell element to it. In order to collect this data, you can see we're heading towards the tornado, and it's kind of coming towards us. And there was a ditch on either side of the road, so I said, just stop the radar on the road. We'll take up a lane, people can get by. Chuck Doswell got heard about this and raised a real ruckus online. I won't tell you what he said about me. It wasn't nice. But we got our data, and no one was blocked. People could get by and around us. Sometimes you have to do things like that. Okay, Chris Weiss then operated the radar, and we had a tornado in near Attica, Kansas, May 12, 2004. And there, by the way, is Chris Weiss in motion. I see Chris Weiss moving really quickly up here. Another tornado. But what we did was we took the radar and scanned up and down, with the tornado across the field of the radar. There was a bore-sighted video, so we knew exactly where the radar was looking with respect to the cloud feature. And what you could do here is you could find out how does the wind vary as a function of height. And the thing that has been seen many times again, and I know Josh has done this many times, is that you can see that the maximum wind is about between 75 and 80 meters per second. It's only about 50 meters off the ground, and the wind speeds decrease as you go out. So the highest wind speeds are pretty low in the tornado. And then Robin took some of the W-band radar, and she did some ground-based velocity track display analyses in which you assume that you have a circular vortex and so on and so on. And we get some nice radial profiles of the wind in tornadoes. And you can read all that and stop here. Then Chris Weiss and I participated in IHOP back in 2002, and we decided that we were going to look at the dryline circulation with a W-band radar. Why not? W-band, you have great sensitivity, very, very small particles. So we did something we call the rolling RHI, where you do an RHI, but you move. And so as you do that, you can reconstruct. It's like pseudo-dual Doppler analysis in the vertical plane. And look, he was able to, using a variational scheme that Chris developed by himself, with no help from me, just some spiritual help. And you can actually see the tilted vertical circulation across the dry line. Very, very nice work. There's Chris running the W-band radar, and we got several papers out of that. Dust devils. One day in Texas, we were on our way chasing tornadoes, and this giant dust devil popped up in the lower center. So I said, okay, forget tornadoes. Here's a bird in the hand. Let's go ahead and scan the dust devil. And there it is. We got some data, and you can see a ring for reflectivity and then the Doppler couplet. And then we have an example of dust devil A was a one-cell vortex, and dust devil B was a two-cell vortex. We're seeing neat stuff that you see in tornado simulations. We were seeing it in dust devils. And actually, I still get calls for this paper. People who are in other fields, doing dust devils on Mars, cite this paper. And this was just a fun thing we did. And then in 2002, at IHOP, I said, well, let's go out to Tucson and take the radar and look at some real dust devils. Well, look at these beautiful dust devils. The radar didn't work. No data. Okay, more fun, Vortex 2. And there, Eric Rasmussen, Al Moeller, who's no longer with us. You probably know of Al. He was one of the first people to correlate the cloud observations with the radar. He did a lot of training for the National Weather Service. And then in the middle, Ivan Popstefania, who was in charge of the phased array national, I'm running out of it, the National Postgraduate School military radar. I'll say a few more words about that. He was in charge of that. Lou Ricker, again looking smart, ever present. And then upper right, there's a picture that Nick Engver took of me with a Weather Channel person doing a live shot during Vortex. You have no idea how annoying this was. There was a rotating storm going behind my back, and I had to face the camera. And every once in a while, I would do that. It was awful. And then there's Lou Wicker and Josh Werman, and David Dowell, my student, who is one of the field coordinators. And there's Jana Hauser showing off. Boy, she was in great shape to be able to do that. And then there's like the movie Roger and Me, Roger Wakimoto, and Yvette and Paul Richardson. That didn't come out right. Yvette Richardson and Paul Markowski. And then there's Eric Rasmussen, and if you're in the pun, being very sassy. None? Okay, forget it. Jana Hauser had a little stint as a truck driver. And then the lower right hand. You notice these guys have machine guns. And this was during, I'm glad this was then and not now. We took an unmarked exit in the Texas Panhandle. And it was a beautiful, beautiful bridge with sculptures on the side. Nothing like you see in the other parts of the Texas Panhandle. I should have been, and there were no signs. I should have been suspicious. Something weird was going on. I pulled up. I said, okay, deploy the radar. This is the phased array radar. big, gigantic thing. The next thing we knew, these guys showed up with machine guns, telling us our radar was aimed at the Pantex nuclear weapons plant. Well, okay. Now, I would be in Sudan or someplace right now, but no, this was back then, and I explained what we were doing, and we had to get on the phone with Bob Bluth at the Naval Postgraduate School and explain what we were doing, and they got into a big argument over whether we had a right to be there or not. And I said, I don't care. This thing isn't going to tornado. Let's just go. So beware of unmarked, beautiful exits. Oh, these are just pictures of people. Some of my students, and Ed Lorenz and Rich Rotuno and John Brown, in a Vortex workshop in a Silomar, and there are a lot of people noted there. During Vortex 2, there was data collection, 3 radars, Josh's Dow 6 and Dow 7, and the radar that we were using, the phased array radar, MDR50XP, and they all scanned the same tornadic storm. And I said, gee, what a great opportunity to check single Doppler retrieval and compare it to the truth, which are dual Doppler analyses from Josh's 2 radars. So we took Josh's analysis, which is the truth. Actually, we redid it. And then we did various things like do retrievals with 6-second data from the actual phased array radar, or 3-minute, and to see what happened. Of course, when you get down to very, very fine time scale, the analysis becomes better and better and better. So I think when the ARC has some of its can take some of its rapid scan radars, you only need one, and if you can get data every few seconds, or every 5 seconds, or even every 10 seconds, you can actually retrieve a nice 2-dimensional wind field. So we think. And then in 2000, well, actually about 2008, we got some funding from NSF to build a mechanically rapidly scanning radar, but was polarimetric. Up to this point, there was no rapid scan radar that was polarimetric, and certainly not an electronically scanning radar that's polarimetric. So it's a simple radar because it's based on frequency hopping, which had been used in the Eldora, in the airborne radar. So the idea is, if you don't know, you change your frequency enough so that what you get is like an independent sample, but not so much that your antenna is way out of tune. And it worked. It was great. The radar has been many upgrades. The truck changes were done at the ARC, and pretty soon, if not now, it probably should be called RAXPOL 2, but it's with a low-power solid-state amplifier and pulse compression. Jeez. And then, Jana, in 2011, we took RAXPOL out, and we got a big tornado, came near us, and here you see 2-second data. 2 seconds. We scanned at 1 elevation angle only. We didn't do volumes. So it looks like a fluid. You can see it. Really amazing. Can learn a lot about tornadoes. My student, Jeff Snyder, took the UMass XPOL radar data and also RAXPOL data, and had a number of papers in which he looked at polarimetric signatures. The one that's most often cited is this numerical work that he did, where he did simulations of various types of polarimetric signatures. And I look and I see these papers are just always cited. Okay, one more tornado video I'm going to show you here. And this is one I took. Jana was with us then. I think Jeff was probably with us too. And let me come here. I don't want to show you the whole thing. Get an appreciation, which you all know in this audience, of how rapidly the multiple vortices in a tornado change. Look at that. It's changing by the second. You have to have a rapid scan radar to be able to do anything with these. These things are lasting a second or two, some of them. And notice how the condensation funnels near the ground, but not above. And I was just watching this in amazement. But we were all calm. Yeah. And Jana was collecting data. And at one point, Jana said, Howie, you think we ought to get out of here? And I said, how far away is it? She said, something like 7 kilometers. I said, no problem. There's some debris in the air. This was west of Shawnee, just east of Lake Thunderbird. I think the tornado began right near Lake Thunderbird. Anyway, you don't have all day, so I'll stop that. And then this is data that Jeff Snyder and Jana Hauser collected on the El Reno 2 tornado, the second one. This is the one in which Tim Samaras tragically lost his life along with some other people. I'm going to say too much about that. There are multiple vortices that pictures I took on May 3rd, 1999 during the big tornado outbreak. And look how close we were to these multiple vortices. There's no radar signature. There are no scatterers. There are clouds. Notice how in the lower right-hand one, the vortices are all tilted towards the center. We see that in the tornado simulators. But no data. Okay. However, in the El Reno tornado, there were enough scatterers that we could see the multiple vortices on radar. And in fact, you can see there's a weak echo hole associated with some of the individual vortices. You can see the vortex signatures, clover leaves, and the rho HV, where you have individual debris things. We were able to track the vortices around in a circle because we were scanning, I think, only up to 5 degrees or something like that. So you had data every 2 seconds, basically. What's happening above, you say it's probably the same as what's happening below. And that was really neat. And Kyle Thiem, this is Kyle Thiem's thesis. He's now at the Boulder Weather Service office. Then we did a dual Doppler analysis with Dodge City and Raxpol. And there's Roger Wakamoto, who's been coming out with us, I think, for the last 10 years. And he stands there with his camera, and he correlates the radar images with what he's seeing in the photographs in a meticulous, beautiful way. And in this particular case, Zach Weinhoff took the data, and this was for his master's thesis. And we did the dual Doppler analysis. You can see everything happen. In the El Reno tornado, what was really neat was you can see this giant debris signature, greater than 5 kilometers across. We also saw a debris signature in the anticyclonic tornado, and you can see both the main cyclonic tornado and the small anticyclonic tornado and low ZDR for the debris clouds for both of those. We also looked at how the tornado developed. Did it develop upward from the ground or downward? Anyway, you see a mesocyclone at about 1 kilometer below the mesocyclone, followed by the appearance of high shear at the surface. So the tornado then, when the mesocyclone then develops a tornado underneath it near the ground, and that gradually builds up with time in this particular case. Now, we also, I think this was during Vortex, the second year of Vortex, we also had a Doppler LiDAR mounted on the phased array radar, co-located. And the Jana was driven crazy by this for a while. The LiDAR was very flaky, but we tried to get tornado data with the LiDAR, and we never could do it. The LiDAR could only see out to maybe 5 or 6 kilometers, and the tornado was always just beyond that. And we could see the tornado in the radar data, but we did see streaks that some people call worms. This is some work that Paul Markowski has done. I think Robbie is doing something with this right now, but we could see these streaks in the Doppler velocity with the Doppler LiDAR. But I understand that NSSL has actually succeeded in getting Doppler data in a tornado, and that's Spirit Experiment. Now I'll let whoever's doing that talk about that sometime. But it's great to have been able to do that. This is some work that Vivek Mahali done, and we had a CASA network, a network of X-band polarimetric radars, closely spaced in different cities in central Oklahoma. And then one day, remember, I got up in the morning, and the tornado, I knew my NOAA weather radio that the tornado warning was going off. I said, it's 7 o'clock in the morning. what's going on? And it turned out there were these mesovortices, which tend to occur at night in a mesoscale convective system, and they pass within the network. And they also pass near KOUN and KTLX. So this was Vivek's master's thesis, and very nice serendipitous thing. Owl horn echoes. Okay, this is Matthew Kramer's master's thesis, and Matthew, by the way, is the SU at Pittsburgh, and I should mention that he composes madrigals, and he used to sit in back, and when nothing was going on, he'd be writing music for choral music. Wonderful. Anyway, after storm chasing for a while, I saw that it looked like these things that looked like owl horns. There was counter-rotating hook echoes. And what's going on here? This reminded me of an old paper from 1976 by Les Lemon that appeared in Jazz, some images in old WSR 57 radar images showing vortices shed along the side of supercells. And so I said, gee, this looks kind of like that. Why don't you do something with this? So he did, Matthew did, but we didn't have Doppler radar. The radar at that point was just reflectivity, so he tracked radar echoes to try to get the wind. And then he did some numerical modeling, and he got these counter-rotating vortices. And it turned out there are two types. One is you have a cyclonic, anticyclonic couplet at low levels, and the other at mid-levels you get an anticyclonic, cyclonic couplet. And anyway, we tried to get this paper published, and it's rejected. The reviewers hated it. And the reviewers almost uniformly said, this isn't interesting, but never said anything about the science. Someday we may renew this, try again. Okay, Dylan and Zach did some field work during Pecan 2015. And there's Dylan, who, by the way, is a bowler extraordinaire. If you go down to the main bowling place here in Norman, his name is up on the wall, right? Where is he? His name is up on the wall. You could ask him. He did some amazing bowling. Anyway, we're now talking about storm chasing. We're interested in these nocturnal convective systems that form without a surface boundary. If there's a front, yeah, you can expect convection's going to go up along the front. If there's a dry line, yeah, it's going to go up along the dry line. If there's an outflow boundary, yeah, you can understand why there's convection. But what a mystery. Why do these storms come up? Well, there's absolutely no boundary. Things are homogeneous. So he did a lot of climatological work, Dylan, and we found that most of the convective initiation occurred east of a low-level jet axis. Why can that be? And so the hypothesis is that you have the tilting of Earth's vorticity by the shear above the low-level jet, and that produces rising motion east of the jet and sinking motion west of the jet, and that fits this. Alan Shapiro probably can say more about this after the fact, but that was the hypothesis, and this looks nice. My students are rewarded if you chase for a whole season, and we happen to chase up in Colorado. I take you hiking, and what can be more fun than going up in June in snow? And so there are Kyle and Zach and Dylan and Zach, and we went out to Mitchell Lake. It's a nice trudge up there. A lot of fun. Okay. Something more recent. Selden, Kansas, in 2021. And there's Trey Greenwood, who is working with his computer. Trey's up there, and Trey, I must say, is an excellent writer. Of all the students I've ever had, Trey was one of the few. And it wasn't ChatGPT, I don't think. But I think his second draft was good enough to show to his committee. I mean, it was amazing. Anyway, what's really neat is that there's the tornado in the upper left-hand portion when it was big. But there was a weak echo hole associated with a cyclonic tornado and a weak echo hole associated with an anticyclonic tornado. Now, down below, you can see the picture I took of the tornado and the wall cloud and Roger Wakimoto and Trey and Raxpol. But Sam, we had we were sitting there looking at the cyclonic tornado, which is what you would do, right? And all of a sudden, debris started swirling around us. What's going on? Well, an anticyclonic tornado formed and moved right over the radar. And, of course, we kept collecting data, right? That's what we do. And so you can see Sam Emerson took a picture of the video looking straight up, and I superimposed that on the radar data. You can see that, the mirror image. Really, really neat. Anyway, these papers they're in review. And there's Jake Margraf, who did some of the original work. He was in the Air Force. Okay, Leah, we're getting up to the present. Leah Swinney, who's here, we had a data set that we collected with Raxpol way back in 2011. And then Mike French, and there's the chase dog that ran into the radar when it was hailing to escape the hail. Apparently it was a friendly dog. And we have radar data from NOAA XP and KFDR and KOUN. Leah put that all together, and I can't say too much about it, but an interesting case. And I'm going to bring you up to the present. This is work my current graduate student, Amiya Nayak, is working on. And what he's trying to do is try to separate the motion of the debris from the motion of the air, or at least the motion of water droplets, which are pretty much moving along with the air, in a tornado. So back in 2024, we were able to collect spectra. Now, to collect Doppler spectra, you forget about frequency hopping, and you forget about rapid scan. So at one point I said, look, we got a lot of nice data. Let's go ahead and try to get some spectra. So we slowed the radar down and collected data, and this is one of the best ones, I think, that he showed. You have the Doppler velocity, and you have the power spectrum in blue, and the cross-correlation coefficient, rho HV, in red. And the cross-correlation coefficient is really noisy. But you can see two peaks in the Doppler spectrum, one which is about minus 10 meters per second, and one that's, like about plus 15, 17 meters per second. And the pink circle shows where this spectrum was calculated, right at the edge of the radar echo, but next to the debris. And what you see is that this negative Doppler velocity, that represents flow coming towards you. So that's the stuff being centrifuged radially outwards. But this peak over here at about 15, 17 meters per second is positive. That represents radial inflow, frictional inflow into the tornado. So anyway, that's what we think. And by the way, here's a picture I took of Amiya, and there happened to be a tornado. He almost eclipsed the tornado picture. All right, I'm going to run through these one by one. I just want to show you an example of research not explicitly covered by a grant, not part of a student's thesis research, just for the hell of it. And Lance Bozart calls this something else, which I thought repeat here. But I was interested in how the low-level shear changed before sunset, 6 o'clock magic. And we found, and this is work that Dylan did for me, he took the Oklahoma Mesonet data and we averaged it over a long period of time as a function of time of day for all these stations from eastern Oklahoma, western Oklahoma, and a Texas network. And we found that the vertical shear vector turned in a counterclockwise direction in time. And I'm going to show you on the right, you see Alan Shapiro's analytic model. I'm showing that because it's so nice and clean, but real data, a lot of data from reanalyses show this. The shear vector rotates the other direction. And I said, what's going on? I went to Rich Rotuno at NCAR, and Rich said to me, Howie, you made a mistake. Your data aren't good. Something's wrong. And so I went back and I checked, and I do what you're supposed to do. Forget about the computer. You go back to the raw data and you look at it, and no, what Dylan was doing was right. And it turns out that It's Rich ran the model, try to simulate this, and it's really due to the sudden cessation of vertical mixing. But you still have the surface drag at the surface. Go read the paper. There's Rich, by the way, posing, skiing left. What's the relationship between overshooting tops and a tornadic supercell and its radar observed resolution? This is for Cameron. And I said, just for the hell of it, we caught a tornado forming one day up in Kansas. And I said, why don't we go ahead and correlate the radar echo top, the weak echo hole aloft, the ZDR column, and the IR top track. We went to Dan Lindsay at Sierra. We put this all together, and on the lower right-hand corner, you can see that the satellite top is always to the left of all the other things. Okay, I'll leave that as something for you to think about. Also, we correlated the multi-cell versus supercell period in the storm, and you can see how the top of the storm has the really lower IR tops just about the time the tornado forms, okay, as you would expect. Doug's behavior. We had data from the NOAA 404 megahertz wind profiler network. I'm sorry I'm keeping you so late. I've got to get this out. And this is where you say, this is a fun exercise. I'm teaching synoptic meteorology, and we talk about the geostroke momentum approximation. How good is it actually? Yeah, you can go to a model, but why not look at real data? Well, you can't do this with a standard observational network. Soundings are released twice a day. But with the NOAA wind profilers, you get really high temporal resolution. And so we were able to calculate all the terms. Look at the paper, you can see what the results were. To the dark side, I spent some time numerical modeling. And while I was on sabbatical, I went to Morris Wiseman. He taught me how to run the Clempin-Wilkinson model. There's Morris in 1984. Do you recognize him? Okay. And what I did was I said, let's put in some bubbles, space them along a line, and vary the angle that the vertical shear makes with the line. And this was something that Doug Lilly at one time had suggested, but I wasn't aware of. And then I became aware of it. So we did this experiment, and the storm splits and you get collisions between storms. But the answer is that when the shear vector is perpendicular to the boundary, you get a lot of interacting storms. It's not good. When the shear vector is along the line of forcing, that's also not good. But when the shear vector is 45 degrees from the line of forcing, that's when you can get right-moving storms to move off without colliding with any left-moving ones. So I think the SPC has made reference to this. I don't know, maybe not, but I thought they did. But this is an interesting work that we did because it shows that you can't actually apply this to real data probably, but it shows you that as storms go up along a boundary, the angle that the shear vector makes with respect to the boundary can be important. And then Dylan did some work using the CM1 model, in which he related, and I know Chris and some of the students had done some similar things, trying to look at gust fronts and try to find out how much vertical motion you can get depending upon their slope and so on. This is important if you're trying to figure out whether air can be lifted up enough along a boundary to initiate convection. How subsidence for convective system can dry out over minuscule area and suppress CI. This is another one of my just for the hell of it projects. Upper left-hand corner, the SPC had a big bullseye over western Oklahoma. Boy, things are going to be really great. And nothing happened. And I noticed by looking at the Oklahoma measurement data that this dry air, pocket of dry air formed and then overspread all of the area that SPC had outlined. And what was happening was that there was subsidence underneath some elevated convection that popped up downstream from some supercells. Man, this is complicated. You talk about predictability. Just want you to appreciate that how complicated the real atmosphere is. Another project we did just for the hell of it, And this was the only project I've ever had which is funded without reviews. It was under this small business grant. And I said, a person by the name of Steve Moore got a hold of me and said he could get an IR camera from FLIR company, and we could use this to map out temperature. I said, sure, temperature gradients and supercells are very important. People have found a great lens to do it. Let's see if we can do it with an IR camera. And I gave it to Robin. Robin ran with it. And there's Robin sitting on the W-band radar. And you can see some of the bore-sighted camera and visual and IR. And without going into any great details, you can read the left-hand corner, the summary. But not surprisingly, you get a bistadiabatic lapse race along a funnel in a tornado. Big surprise. But it's neat to be able to do it. Anyway, this is not a really practical thing to do because if there's rain or dust intervening, it follows up your movements. Greg LaMiller, one of my students, he was a semifinalist in the 1999 Van Cliburn competition. This guy was brilliant. Then he went to work for Enron and got out of Enron before it collapsed and then made a fortune. Smart guy. And unfortunately, he's no longer with us. But I noticed that in May of 1998, which was a terrible chase year, that a mesocyclone from a supercell passed right over the Lamont Doppler wind profiler. Another great opportunity. I said, Greg, do something with this. And he did, and he was able to. You have the vertically pointing data. You can see the updraft as the mesocyclone passes by and how it relates to the hail and so on. A fascinating little paper that he took the opportunity to do it. Here's another case that I did with David Dowell. We weren't really funded to do this. I mean, I could justify it. But a storm came up over Arcadia in northeastern part of Oklahoma City, east of Edmond, and they happened to collect dual Doppler data with a Cimarron and Norman radar. No one ever looked at this. And I said, you know, it's right near the WKY instrumented tower. That storm probably went right over the tower. Now we can compare dual Doppler analysis to what the in situ measurement in the tower says. It's a function of height. And we did it. And there you can see it. You can look through the paper to see what happened. A fascinating little study. Jana, for her master's thesis, I wasn't funded at all to do this. I said, you know, we just had a snowstorm here in Norman, and there were all these waves going around. I wonder what they are. And maybe they're Kelvin Helmholtz. So Janet took this and ran with it. And you can look at this, and you can see we did dual Doppler analysis between KTLX. Jana, did dual Doppler analysis between KTLX and KOUN. And it's really neat to see what happened there. As NASA impacts, or what it's like to spend 8 hours or more in a closed radar without any heat while the winds are gusting to 70 miles an hour and it's snowing like hell. Who could you want to do this with? David Schwartzman, best person in the world. I was getting excited about the weather, looking at the radar. David was trying out different scanning, different waveforms. He was having a grand old time. And it turned out that there's the radar. We couldn't get to it in the morning because it was underwater at high tide. We had to wait for the tide to go out. So we get to the radar. This is parked right in the ocean at Plymouth. And we did get some vertically pointing data as a function of time. I'm not going to talk about it, but this was great fun. And I'm supposed to write a paper. It's been 2 years, 3 years, 4 years, 3 years. I still haven't done it, but I will get to it. Promise. Another thing, just for the hell of it, by going to Boulder, Colorado a lot, I got really interested in mountain waves. The lenticular clouds are spectacular. You get these windstorms. And so I started to take a lot of pictures. And I said, you know what? I've got 20 years of these pictures or more. Why don't we correlate the type of cloud you see with the atmosphere environmental conditions upstream from Boulder? And so I had some undergraduate students, Simon Lee, Karen Pope, and Matthew Holliday. Are any of them here in graduate school now? I thought they were. Anyway, and this paper was rejected also, and for good reason. It's very, very difficult to get representative soundings. Sometimes these clouds only in one location, and they don't last for very long. But it was a great experience. But in 2001, Pete Luptic, with money funded from Climate, did a study of polar windstorms. And then in 2008, it was refined by Andrew Mercer and Mike Richmond, who was a statistics person, faculty here, and got together and got a paper on statistical modeling of downslope windstorms in Colorado. Won't say anything about that, but it was a lot of fun. So here's a quick addendum. I didn't want to pick every paper that I've ever been associated with. I can't do that. I'm not mentioning a lot of people. But sort of like the proof of Fermat's last theorem, no time to show it, it's in the margin. I'm just going to name some of the interesting projects I've been working on, just so that you can see what kind of interesting stuff you can do out there. Okay, I came up with the name LP for LP storms. And after Bob Davies-Jones and Don Burgess came up with the name dryline storm to talk about these storms that didn't produce very much precip. And then Chuck Doswell picked up on high precipitation storms, which are the opposite. And now we have the whole spectrum. Landspout. I may not be the person that invented this, but I remember I was the first person to get it into print. I have no idea. Someone may have said it. But it happened one day when we were going out storm chasing. This, again, is serendipity. We were driving off to Texas where there was a supercell. And on the way, I turned to the back, the radar truck, and out the back of the window, I saw a tornado. Now, you're not doing a very good job when you're going one direction to see a tornado, and there's a tornado out the back window. Happiness is a tornado out the rear view window. There are other things you can put in there too, which I won't say. But happiness is seeing a tornado out the back. Well, we had People magazine with us, and they were trying to do a story on us. So I said, okay, we're never going to get down to Texas. Here's a bird in the bush, a bird in hand. Let's go ahead and look at it. And I noticed, this is very odd. There's a tornado out there. There's no precipitation. The tops of the storms are nowhere near the tropopause. And then I remembered some work that Don Burgess had done on these storms that where the tornado appeared before there was precip while the storm was growing. This is one of them. And I got all excited. And the People magazine, we got out of the car to take pictures, said, Howie, point to the tornado and look frantic. Or excited. I said, Okay, Cameron mentioned the formation of squall line papers. Prefrontal troughs, I got all excited about these prefrontal trough features, talk about that in my synoptic class. And then Brian Cawley and David Schultz and others really did a much better job than I did, took up in this and explained these. Multiple Doppler radar observation, mobile Doppler radar observations, fronts, that's what you do when storms don't form. You go out and the storms gust out, and then you notice there's a really strong cold front coming your way. Let's stop and collect data. And that's what we did. Got a paper out of it. Possible conditional symmetric instability in tropical cyclones and their possible role in producing strong updrafts and downdrafts. I mean, we're talking 10 meters per second in hurricanes. And Frank Marks came over to me and said, Howie, what do you think? And I looked at the data and I said, gee, I wondered that if you did some of Kerry Emanuel's analysis of conditional symmetric instability, but did it in polar coordinates, what would happen? Well, people had already thought about this. I wasn't the first person to do this, but I applied it to the radar data we had. And yeah, the necessary conditions for CSI were there. Let's see. Move on. Bluestein and Gorman. It's one of my few forays into lightning activity, and we correlated lightning activity with the structure of a tornadic supercell. In 1988 and 1994, I had noticed these high base funnel clouds in the storm chases. I think the only one I'd ever heard anything about this was from Chuck Doswell. So I documented a lot of these. I haven't been explained completely yet. Freddie Parker and I did a climatological analysis of the modes of CI along the dry line. One day I was hiking by myself, and I sat down to have lunch, and I was about 12,000 feet. And I looked there was a tornado off to the south. What do I do? I couldn't believe it. I got back to Boulder, and I checked the Doppler the radar, and there was a supercell down there over the mountainous terrain. And so I documented it, and then Morris had me take the Colloquium model, put in the environmental sounding, and yep, you got a supercell, even if you started it at 700 millibars. Okay. And then this thing I call downscale transition. I noticed that sometimes you see the towers in a supercell get narrower and narrower and narrower as they dissipate. Whereas usually what happens is they rain out and you go upscale and you get a big area stratiform piece of. I collected a lot of pictures. It was a note, a picture of the month, and this was published. Anyway, I thought that was interesting. I'm getting near the end. 1, 2, 3, 4, 5. 5 books. My Synoptic Dynamic Meteorology book was 2 volumes. It took me over 10 years to write that. That came out in 92 and 93. I started doing it in the early 1980s. And it based it on Fred Sanders' notes, brought up to date, included some mesoscale meteorology with Lance Bozart, Kerry Emanuel, and Dan Kaiser's influence. And the synoptic book that people used back in those days was Pedersen, 1959. I mean, there was a crude version of quasi-geostrophic theory in there. So I took it upon myself to take my lecture notes over the previous 10 years and come out with these 2 books. Then in 2013, I realized there was a need for a convection book. Kerry had a beautiful book in 1994 that was highly theoretical. And I said, I'm going to do the same thing, but I'm going to put in some photos of my own and radar images. And that came out in 2013. This book is so expensive that most people don't want to buy it. It's crazy. It's over $200. And then, when I was at one point I said, I ought to just take my pictures and say something about chasing history. This became Tornado Alley. And this has sold way over 10,000. It sold over 10,000 copies 20 years ago. So I don't know probably not doing very well now because it's been out for a long time. And then I decided to update Scorer's 1972 book, Clouds of the World, and go through all my cloud photographs and come up with something. And this came out in 2024. So I'm going to end with some summary and advice, especially to students. Okay? This is a Lance Bozart quote. Pay attention. Constant, careful, critical observations take advantage of what's available, what I call meteorological bricolage. So you're taking the stuff that's out there and you're putting it together. And that's what we did with a lot of our studies. An interesting event happened, and someone had a radar here and someone had a profiler over there. Put it all together. Don't let anyone tell you can't do something if they cannot convince you that you're wrong. Just do it, even without funding if you can. I've heard people moan and complain, I can't get funded to do this. What? Figure it out. Go ahead and do it anyway. Get a small pot of money. Just do it. Rob a bank. No, just kidding. Yeah. But just do it. Okay. Important. Do something you find exciting and intriguing. I'm glad that this was mentioned earlier. Don't mass-produce papers just to get large publication records, even though others may judge you by your production rate. Make sure some of your papers, and this is important, this was advice given to me by Yoshi Sasaki, make sure some of your papers reflect mostly on your original contributions and be the lead author of these. Do some dirty work yourself. All right? So in other words, it's nice to have 20 authors, co-authors on your paper, but you have to have some where it's your idea, or you just have a few co-authors, but it's your idea, and you want to get most of the credit for it. But on the other hand, do be nice people, help others, collaborate when possible, and this increases your publication rate. You can have it both ways. You can collaborate and get multi-authored papers and run up your publication rate, which everybody likes, but make sure you do something by yourself. Okay, look ahead to the long term. Don't let current political and budgetary situations dissuade you. Political and economic disturbances are like colds. You get back to normal eventually, right? The government reopened today. Don't get me going. Consider the effects of AI on your topics of interest. Be ready to harvest benefit from it, and don't ignore it or dismiss it offhand as something detached from theory and observations. I often say, oh yeah, I don't know, why is it doing this? Why is it giving me this result? Well, there's something there, and you should figure out. It's a very, very important future in meteorology. Figure it out. Figure out how to do experiment with it if you're going to learn something. Don't just poo-poo it, as I used to do. Enjoy yourself. Have fun. Don't be one-dimensional. Cultivate other activities other than your paid work. You know, I have my students who are pianists and musicians. Jen, I think you were in an orchestra. I know a lot of you I haven't mentioned are musical. And some of you hike. And folk dance. Dushan and I used to folk dance a lot. Just do something other than what your work. Have something else that's a lot of fun. Look at other ends. Right? And above all, I put this in red. Be honest. Don't fudge your data. And this is hard if you have a preconception of what you think your data is supposed to show. Be honest. Don't fudge your data. Admit when you're wrong and move on. And I can now sing the song from 1936, Pick Yourself Up, Start All Over Again, famous Fred Astaire, Ginger Rogers movie. Okay, some of you are nodding your heads to be polite. I don't know. Okay, I'd like to thanks. I want to give great thanks to especially all my students and collaborators, who a lot of whom were already mentioned. I want to give special thanks to Cameron and Lindsay, and I presume the Dean's office, the money didn't fall off a tree, for funding and organizing this event. I have to thank NSF for giving me almost continuous funding since I got my first proposal funded. NOAA, oh my God, NOAA I owe a lot to for letting me go up in their airplanes and collaborate with their people. NASA for the same thing. NSSL, my God, I came here in large part because NSSL was here, responsible for getting us into this building, building up the department, hiring people. Fred Carr, my good friend, who's now off in South America. Joe Friday, who was the head of the National Weather Service, who personally helped me and was an advocate for me. David Bourne was an advocate for me. Ron Taylor, Brad Smell, Chungulu, Nick Anderson, or NSF. I want to mention, this sounds like an Academy Award thing, doesn't it? It's not meant to be that way, but Joyce Berry, who was my editor at Oxford University Press, who was kind of like Robert Gottlieb. I mean, she was the only editor I've ever had who went over my text and said, this is bad, this has to be fixed. Now, when you go to all the books I've had recently, the editing has been minimal, and I know my books aren't great. Ask my students. And let's see, Sean and Mark Laufenschweiler for others for their IT support, and then Chris, Rob, and Jeff, and others for teaching an old guy Adobe Illustrator, Photoshop, Solo. I mean, they taught me how to do these things. And finally, my wife, who is an emeritus professor of English, Kathleen Welch, she gets honorable mention for putting up with me for how many years has it been? 30, 39, 30, up the upper 30s. It's enough. And you know what it's like to be married to someone who you never know if they're going to come home. And she never knows what I'm going to be doing. And I say goodbye, and I run out the door. And she throws parties at our house, and I don't show up, or I show up as the party is ending. Or I come back at 3 o'clock in the morning with fast food on my breath. Finally, a picture that Ming Wei took, and this is what I enjoy doing the most. Those of you who know me, eating is very important. This is an orgy. Chinese food covering the entire plate. And man, that is great fun. And then finally, I'm going to leave you with one last picture. My God, it's late. This is Wednesday night in Norman, Oklahoma. And I went out, not Wednesday night, what am I saying? This was Tuesday night. And this was Lake Thunderbird. And I knew where to go because I went out there during the last aurora. But it was just gorgeous. You could see it with the naked eye. And then Kerry and I went out to Lake Thunderbird last night again. We saw the aurora, but it wasn't great. That's all I have, folks. I'm sorry I kept you so long. I had a lot to get out. Thank you, and legacy. Thank you. I'm continuing to chase. I'm continuing to do works. I'm not going that far away. So you'd be sorry for it.
I did want to provide an opportunity if anyone wanted to ask Howie questions before we left the room. I know it's a bit late. I'll just quickly say I, for one, am very sad that I missed the George era. That seemed like an ideal time. Any questions? Want to answer?
You're all exhausted.
All right. Well, you linger, come talk to Howie, and thank you all for coming today. Appreciate it.
Yes. I never even put on my sport coat. I forgot that. Yeah, screw. I'm really sorry. I know I went so far over, but there's just so much a lot of the stuff I've never given seminars on. Yeah. The people don't know about it.
Yep. So 48 and a half years. That's, yes.
Oh, well. Don't tell me about when I have to get out of my office yet. But I will try when I come back in the spring.
Yeah, no.
I probably will end up throwing out all the journals.